Hello everybody, this is Dr. Christopher White, and in this presentation we're going to continue thinking about earthquakes and the Earth's interior. So in this video we're going to be looking at how does faulting cause earthquakes, and this is going to correspond to section 12.2 of your textbook. So as you can see here, we have ourselves a diagram of a strike-slip fault. So we can see we have one block over here marked out in the medium grey colour, and we have one block over here which is marked out in the kind of brown grey colour. And so the fault plane is going to be coming along somewhere in that orientation. Now, as we've already discussed, these two blocks of rock want to move past each other because tectonic force is being applied to them, and that tectonic force is trying to make them move past each other, but they won't because of friction. So what happens is this energy is being constantly imparted into these blocks of rock to try and make them move, but they're not going anywhere. So the amount of stored energy begins to increase over time. So as we can see here, what's going to happen over time is we're going to have the amount of stress increasing, okay, because stress is this is energy being applied to our blocks of rock. And this stress is going to be stored in our blocks of rock as elastic strain. Okay, now think of elastic strain like a plastic ruler. So if you take your plastic ruler and you bend it, it will form an arch shape. Okay, now once you let go of one end of the plastic ruler, the ruler will simply return back to its original shape. So by bending the ruler, you are applying stress to it. So the stress that you're applying to it is obviously in the form of mechanical energy. You're bending it, but the energy you're putting into the ruler is being stored in the ruler as elastic strain. And then once you release the ruler, the elastic strain can then be released and the ruler will then return to its original shape. This is what elastic strain is. Stress gets stored up, it gets released, and whatever essentially had the stress building up in it returns to its original shape. Okay, so don't think of this like folding, don't think of this like faulting where we have, rock getting damaged. In the case of elastic strain, we have rocks deforming, okay, and the rocks are deforming in response to the stress, but once that elastic strain is released, so the energy is lost, the rocks will return to their original shape. So just bear that in mind. This isn't a permanent type of deformation. Okay, so obviously our two blocks of rock want to move past each other, but they can't because of friction. So if we look here, you can see we have a graph. Obviously, we've got time increasing on the x-axis, and we have increasing stress on the y-axis. So you can see that over time, the amount of stress is increasing because energy is being imparted into these blocks of rock, but they can't move past each other. Okay, so what's happening now? Well, we still have our two blocks of rock. They still want to move past each other. And as we can see from the graph here, the amount of stress is steadily increasing. So that means we have more and more energy being stored up in these two blocks of rock in the form of elastic strain. Now, eventually, we're going to reach a point where the amount of stress which is stored is in excess of friction. So once friction is overcome, these two blocks of rock are going to start moving past each other. And this process is referred to as slip. So once the two blocks of rock start moving, they are slipping past each other. And obviously the slip is going to occur along the fault plane because that's the point of weakness. You're not going to start, doing anything weird like trying to move the rock over here or over here. Nope, the fault plane is right there. It's the weak point, and so obviously the movement's going to occur along that fault plane. Now, obviously, once we cause the earthquake to occur, we are releasing the elastic strain that's been building up over time. And so once the strain is released, obviously, we're going to see the amount of stress drop back to the starting level. And then obviously, once the energy's been released, the fault will lock back up. It will stop moving. So the slip will stop. And once slip stops, well, once again, friction's in charge again, and so these two pieces of rock will not be able to move past each other. And so we're going to start seeing the amount of stress beginning to build up again until it eventually gets high enough to cause another earthquake. And this can, occur over a very large range of timescales. Some faults will produce earthquakes, every few years, and some faults won't move over periods of time of thousands or hundreds of thousands of years. So it can sometimes take a very long time for the amount of stress to build up to a level where friction is overcome. Now, this behavior of fault movement and the fault locking up again is referred to as stick-slip behavior. Obviously, slip is when the fault is moving, and stick is when the fault is incapable of moving because of friction. And this is the way that the vast majority of faults will move. They will move typically in short bursts. Now, that doesn't go for every fault. There are some faults that are actually in constant motion, so they don't actually stick, but the vast majority of faults will have this stick-slip behavior, and so they have the capacity to produce earthquakes. Now, most of these earthquakes will be very small, you'll barely even feel them. However, there will occasionally be some earthquakes produced which are very, very large and can cause a lot of damage. So let's think about how an earthquake actually works now. So here once again we have two blocks of rock. They want to move past each other. We can see the fault plane marked out here as this slightly darker brown rectangle. Now, this grey oval here represents the rupture. So this is actually where the fault is moving. So these two blocks of rock want to move past each other, and initially friction is too great to stop that happening, but eventually the stress gets high enough to overcome that friction, and so a rupture starts forming. And so what a rupture is essentially is its deformation along the fault plane. So the fault plane is obviously the weak point. And so obviously once movement starts, it's going to be focused along the fault plane. And so we're going to see all the activity occurring in this region right here. Now, eventually, as our earthquake progresses, the size of the rupture is going to get larger because more and more of the fault will start moving. Initially, it starts off at this point, but as the earthquake progresses, more and more of the fault is going to begin motion. And so this causes our rupture to increase in size. Now, eventually our rupture is also going to reach the surface of the Earth. And when it reaches the surface of the Earth, it's going to form a feature which we refer to as a fault scarp. And this is going to be a noticeable, essentially, line on the surface of the Earth where we see damage to the Earth's surface produced by fault movement. And I'm going to show you a couple of photographs in just a second to demonstrate that. So fault scarps occur when the rupture intersects the surface of the Earth. Now, over time, should I say, during the earthquake, obviously the amount of slip, so the size of the rupture is going to continue getting larger, and so this obviously means the fault scarp is also going to get larger. And eventually what's going to happen is, of course, the fault is going to expend all the energy that's built up. The rocks are going to start moving, and they're going to lock back into each other, and friction is going to stop them going anywhere. So in terms of fault scarps, we have a couple of examples right here. So the fault scarp in this image can be seen right there as this trench-like feature. So this is a fault scarp which is being produced by a strike-slip fault. So the blocks of rock either side of this fault are trying to move past each other. So for argument's sake, let's say this block is trying to move towards you and this block is trying to move away from you. So the fault itself is going to be located right there, and the fault movement has essentially led to the formation of this fault scarp due to rocks getting damaged along the fault plane as the fault is in motion. Now, in this case, we have a similar feature, but it's being produced by a different type of fault. So this fault scarp is due to a normal fault. So in this case, we'll notice the strike-slip fault has essentially just produced a trench. In the case of the normal fault here, you'll notice there's a distinct step, there's a distinct change in topography. The ground is higher over here, it drops down at the fault scarp, and then that's the new ground level there. And obviously that's because we know in the case of normal faults, the hanging wall will drop down relative to the footwall. So this represents our hanging wall block here. This represents our footwall block here. So the hanging wall block has dropped down relative to the footwall block, and that explains why we get this change in topography. And obviously we can see that the fault scarp itself represents once again the location where the fault is occurring on the surface of the Earth. Now, what you'll notice is that the fault scarp is steadily being broken down, because obviously a fault scarp is going to expose rock, and these rocks, the rock that's exposed will naturally weather, and you can see that because we have all this loose material which is being produced by the erosion of the fault scarp. So over time, fault scarps will either be eroded away and lost, or they will get filled in. And so not all faults will have a visible fault scarp. Typically, the fault scarp for a fault is most visible pretty much as soon as the earthquake occurs. That's when it's going to be at its newest, it's going to be at its most obvious, and then over time that fault scarp will steadily either be eroded away or filled in, and it will get lost until the next time the fault moves. All right, thank you for watching everybody, and have a good day.